All right. Uh, the univariate statistics and multivariate statistics, the both are the inferential statistics, right? So in inferential statistics, we never know the population. So we are always a sample, the subset of a sample from the population, right? So we sample the x1, x2 to xn, and we got some sample statistics. And also we sampled another groups and got another sample statistics, and x2, x3, and got another sample statistics, right? So, and then we are trying to test hypothesis testing using the sampling distribution of sample statistics. We don't use a sample distribution. We are using sampling distribution of sample statistics. So that is great because the sampling distribution of sample statistics usually follows the normal distribution. So the particularly mean, right? So the sample mean is unbiased estimator, right? Which means the expected value of a sample mean is equal to population mean. So which is unbiased estimator. So according to the central limit theorem, regardless of the population distribution, the sampling distribution of mean is always normal if you have enough sample size. So we'll talk about that later. Then, so the population consists of the total of the observation, and the sample is a subset of a population, right? So, and this is most commonly used the sample statistics. So for the mean and the population is we are using mu, and variance is sigma square, and the sample is x bar, and this is the sample variance, right? So these are the sample statistics, and these are the population statistics. So based on these sample statistics, we try to make inference the population statistics. This is inferential statistics. So this is a statistic. Statistic, not S. Statistic is a function of a sample. So this is the mean, right? This is variance. Sample variance. This is the sample variance. This is the sample mean. So if you add them up, all the values and divided by n, this is the sample mean. And then this is the sample statistics, a sample variance, right? So we are 1 over n xi minus x bar square. This is deviation, right? So this whole part is the sum of deviation, And then in population variance, the we divide by n, but in sample variance, the we divide by n minus 1, right? Because the sampling distribution of a sample no, I'm sorry. Sampling distribution of variance is a biased estimator. So which means expected value of, I'm sorry. Expected value of sample variance is not equal to the population variance. So this is biased, right? So to correct the biasness, we use n minus 1. So I will show you later so how it works, okay? So this is mean and sample variance. So sampling variance is the distribution of a statistic, right? So two important statistics. So it is distribution of mean and sampling distribution of mean and sampling distribution of variance. So what is the distribution of a sampling distribution of a mean? This follows normal distribution, right? But what is the distribution of a sampling? What is sampling distribution of the variance? Any idea? It also follows normal, but it is biased. So for example, this is normal, and we sampled it, right? We sampled x1 and we, for example, x1, x2, x3, xn, and let's say this is x1, x1, x2, x3 to the xn. This is x2. Every many times, if the average of these sample mean is equal to the population mean, right? So that is the unbiasedness. But sampling distribution, the variance of a sampling distribution is always smaller than the population variance. So this is a biasness. Okay. So first, let's talk about the sample mean. This is the sample mean, right? This is the summation. So we add all the variables, observations, and divide by n, right? So this can be expressed by the expected value of x. So expected value, this is theoretical average. So if we repeat, for example, the head and tail, so we flip the coin, we toss a coin, and what is the probability of, if you toss 10 times, what would be the probability of getting head? Maybe first time we may get 7, when next time 3, right? So and then if you do it again, maybe 4, 6, 2, 8. But if you do many times, we will approach to 50% and 50%, right? So this is expected value. So expected value is the theoretical, the average, okay? So expected value is the just average of theoretical. So in this case, the reason why I'm showing this expected value in the multivariate statistics, you will see expected values many times. So first, so expected value of this one is the x bar. This is n over x1 plus x2 plus xn, right? So this is, and then 1 over n, this is a constant. So it's go outside. So n over ex1 plus n over 1 ex2 plus n over 1 exn. Okay. And then n, this one is expected value of x1. This is what? This is mu. This is population mean, right? So because the mean of a random variable is equal to population mean. So this one is same plus n over, this is mu. So how many n times, how many n we have? N times, right? So n times mu. So n mu. So expected value of a random variable is equal to the population mean. Okay. And now let's talk about the variance of mean. So variance of mean, this is variance of n over, what is that? X plus x2 plus xn, right? And then 1 over n, this is constant. The variance is a squared value, right? So it will go out. When it goes out, it will be squared. And then variance x1 plus variance x2 plus 1 over n squared, and the variance xn, right? And then variance of x, this is sigma square, right? Sigma square plus n square 1 and sigma square. Do you follow me? So how many n we have? N square, n over 1, n 1 over n square. We have n, right? We have n over square, 1 over n square, and times. So it will be sigma square times n. Okay, so this why the sampling distribution of mean follows mu n, right? You learned this one from the Univariate statistics, right? So the sigma squared divided by n. So this is a variance of the mean, okay? All right. And then if the population distribution is, oh, I'm sorry. If the population distribution is this one, and then random variable x1 through xn are follows IID. IID means independently, identically distributed from this distribution. So the x bar, this is mean, right? The mean of the population distribution follows the distribution. I just show you, right? Mean would be mu and deviation. This is variance of x bar, and this is mean of x bar. And also the z distribution follows this one. So x mu minus x bar minus mu and sigma n1, because variance of x bar is this one. So standard deviation is if you take a square root, it will be this one. Okay, it will be distributed in a 0 and 1. Okay, and then central limit theorem. The central limit theorem is just very, very important theory, right? Because regardless of the random sampling, so for example, we have a population, this is a population, and then we sampled one x1 through xn, and then get the mean, and then another sample, get the x1 through xn, get the x2 mean, and x3 mean, okay? And then these sample means will be a normal distribution, right? So even though our population distribution is a uniform distribution or positively skewed distribution or negatively skewed distribution, it doesn't matter. If our sample size is greater than 30, okay, so this sampling distribution will be will approach to the normal. Okay, so that is a central limit theorem, right? So if x2, x2n is a sequence of independent, identically distributed random variable with a mean and variance, the distribution of their average x is followed by this distribution, right? Mean is mu, and standard variance is sigma squared divided by n for large n. Generally, n is greater than 30, it follows normal. So the 30, n is 30, so which means we will sample more than 30 people, okay? Not 30 different sample, okay? Sometimes the students are confused about that. So n is more than 30 observations. Okay, so and then sample variance is this is the sample variance, right? Sample variance follows. Okay, let's say this is minus x bar square. This is a population variance, and this is a sample variance, right? So, like I said, the variance sampling distribution of variance is unbiased. So we do m minus 1 here, and this is degrees of freedom, right? So why do we put m minus 1 here? So theoretically, x1 minus x bar, this is deviation, right? And plus another deviation. So I'm doing like this part. 2 minus x, 3 minus x bar plus xn minus x bar, okay? And this should be 0, right? So sum of deviation should be 0. So, and then mean is, this is constant. We have n times mean, right? So x1 plus x2 plus xn, this is n times x bar. Okay, so these x1 through xn minus 1, these numbers are free to vary. Any numbers that can be entered, right? But this number, last number, is fixed, right? So how many numbers are free to vary? n minus 1. So this is degrees of freedom right here. Okay. So, and this is important. And one more important concept. The sample variance follows a chi-square distribution. Okay. So the basically chi-square distribution is n minus 1 variance and this one. This is chi-square distribution. N minus 1 is, this is the degrees of freedom. Okay. So here, as you can see, we can change this value. For example, if I multiply n minus 1 here, n minus 1 and n minus 1, right? It will cancel out. And then this part is right here. And this part is right here, right? So, and n chi-square distribution is n minus 1 times sample variance over population variance. So if we divide by population variance, it becomes chi-square distribution. But n minus 1 and this one is constant. So it really doesn't affect the distribution. So sigma s square sample variance is follows the chi-square distribution. Okay. So assume x1 to xn, and this is IID, the normal distribution. So this is distributed chi-square n minus 1 here. So this is the sample variance is follows the chi-square distribution. Follows chi-square distribution. Okay, so we'll talk more about the chi-square distribution later. Okay, and t distribution. So the t distribution is this is very similar to the z distribution, but actually t distribution is a combination of z distribution and chi-square distribution. This is definition of t distribution. So t distribution is defined by the z over square root chi-square divided by degrees of freedom. So this is z distribution, and this part is chi-square distribution. Okay, so put it differently, t distribution is scaled t distribution. I'm sorry, t distribution is scaled z distribution by chi-square values. Okay, so the t distribution has degrees of freedom, right? So this is the sufficient statistics. So t distribution is determined by degrees of freedom. And what is the mean of t distribution? It's 0, right? So, and then it has a longer tail than the standard normal distribution. So this is the standard normal distribution, 0 and 1. right? But it's pretty similar to the Z distribution, but T distribution is shorter than Z distribution, and it has a thicker tail, right? But if we increase the degrees of freedom, it will approach it to the Z distribution, okay? If a DF increase, the T distribution to approach to the Z distribution. As you can see, when this is degrees of freedom K, when degrees of freedom is 1, T distribution looks like this, and this is a Z distribution. But if we increase degrees of freedom, it approaches to the Z distribution. All right. So which means if we have a really, really big sample size, the actually t-test and z-test is not different much because the t distribution approaches to the z distribution. Okay, so this is t distribution. Like I said, t distribution is z distribution and y over the degrees of freedom, right? So z distribution is right here. And then square root, and the chi-square distribution is right here. And then degrees of freedom is right here. So the t distribution can be defined by like this. If you calculate this one, you will get this one. X bar minus mu divided by sample standard deviation over square root n. Okay, this is t. What is z? Z is x minus mu and sigma over square root n, right? So what is the difference here? This one and this one. These are different. So so the Z distribution use population standard deviation. So if you know the population standard deviation, in that case, you can use the Z distribution and Z test. But in many cases, most cases, we never know the population standard deviation, right? That's why we need a T distribution. So here, so this is the sample standard deviation. So we are using the sample standard deviation for T statistics. So this is the main differences between these two. And also T follows the T distribution with degrees of freedom n minus 1. Okay, it's the same. Right, so and then chi-square distribution. So chi-square distribution is a chi-square distribution is related to the standard normal distribution. Okay, so this is the standard normal distribution. And if you square it, that is x minus mu square and this one, right? And then if we add another chi-square, no, I'm sorry, the squared z distribution, that is x2 minus mu square and this one, right? So squared z distribution follows chi-square distribution. So if you add all squared z distribution, it will follow the chi-square distribution. Okay. So this is the squared z distribution, squared z distribution. If you add them up, this is the summation of a squared standard normal. It will follow chi-square distribution. So this is a chi-square distribution, the formula, we don't need to memorize that, but it uses gamma. So it uses gamma distribution. So gamma distribution is very similar to the chi-square distribution. Okay. So the chi-square distribution is a special case of gamma distribution. And the mean is degrees of freedom and variance is 2 times degrees of freedom. For example, okay, chi-square distribution with the degrees of freedom over 5. What is the mean of this chi-square distribution? The 5. Okay, so mean is degrees of freedom, and the variance will be 10, 2 times 5. Okay, so this is basic concepts, characteristics of chi-square distribution. Okay. So So sampling distribution of a variance follows the chi-square distribution. Also likelihood ratio test. So we'll talk about that later. The likelihood ratio follows the chi-square distribution. Okay. And this is a Z distribution, right? Z distribution. And if you square it, if you don't believe me, you can square every single values and plot it. You will get this graph. Okay, this is chi-square distribution. Okay, again, chi-square distribution is a Z squared distribution. Okay, and then minimum is always 0, and it is positive infinity, right? So range is 0 to positive infinity. So we don't have a left tail. So chi-square test is always the one tail, the positive side. Okay. Right, this is chi-square distribution. So if degrees of freedom is only 1, this is almost like exponential function. But if we increase degrees of freedom, it becomes what? Normal. Okay, so chi-square distribution is determined by the degrees of freedom. So only single parameter. So this is a sufficient statistic. Okay, and one more. And F distribution. So F distribution is ratio of chi-square distribution. Okay, so this is F statistics. And then this is chi-square, the first chi-square distribution divided by degrees of freedom. And second chi-square distribution divided by degrees of freedom. So the F distribution is ratio of to the chi-square distribution, chi-square value. Okay, so we have two degrees of freedom, V1 and V2, right? And also we use the upper tail. So F distribution is very similar to the chi-square distribution, right? But we have a 2 degrees of freedom right here. Where minimum is 0, the maximum is positive infinity. So it always have one side, the right tail test, right? So you already learned about the F distribution and F statistics. For regression test, ANOVA test, we all use the F distribution, right? So when we test the general model fit, we test F test, right? Okay, any questions so far? This is the basic concepts of continuous distribution. No? Okay, we'll move on to the random variables. So when more than one random variable is present, there are several different types of statistical distribution. So univariate statistics. Okay, let me say. We have 3 different distribution. First one is a marginal distribution. Second one is joint distribution. Third one is conditional distribution. So all the univariate statistics is related to the marginal distribution. This is the univariate statistics. But the multivariate statistic is related to the joint distribution. Okay. And let's think about this case. We'll first consider 2 discrete random variable first. So in this case, X is outcome of a flip of a penny, and Z is the outcome of a flip of dime. And then we assume these 2 events are independent. Okay. So what is the probability of head of a penny is a 0.5, right? So what is the probability of a tail of a penny is a 0.5, right? And what about this case? So the head for dime is 0.5, head for a tail for dime is 0.5, right? So do you understand this one? Okay, so the marginal distribution is the distribution of one variable only. So in this case, fx or fz. Okay, fx is for penny, fz is for dime, right? So marginal distribution is only for one variable. So this is a univariate distribution, right? So joint distribution is x and z. So this is a distribution over both cases, both variables. So both x and z, okay? And then what about the conditional distribution? This is a distribution of one variable conditional on values of other value, the other. Okay, so f x given z or f z given x. So which means the distribution of x given z, the distribution of a one variable given another variable. Okay, so this is conditional distribution. So the marginal distribution, like I said, the marginal distribution is a distribution of only one single variable, right? So, you know, the univariate statistics always follows a marginal distribution. Okay, so but joint distribution describes the distribution of more than one variable simultaneously. So in this example, in our example, so the distribution of when penny is head and dime is head, we consider the two cases, right? So f, x, and z, or f, x, and z. In this case, the penny is head, dime is tail, and or penny is tail, or dime is head, or penny is tail, or dime is tail, right? So in this case, we are considering some interactions between these two different variables, right? So this is a joint. So we will use joint distribution to introduce two topics later. So joint distribution of an independent variable. So I will show you how to conduct independence test using joint distribution, and also maximum likelihood estimation. They also use joint distribution. So you need to understand these concepts, okay? Joint distribution and the marginal distribution, joint distribution, and conditional distribution. So this is an example. Random variables are said to be independent if the occurrence of one event makes it neither more nor less probable or another event. Let's think about this case. This is dime and penny, and I made a 2x2 contingency table here, right? So this is x is equal to the when penny is head, and I'm sorry, penny is head and penny is tail, and dime is head, dime is tail, right? So in this case, so we can see this case is penny is head and dime is head, and penny is head and dime is tail, right? Also, we can see The penny is tail, dime is head, and penny is tail, dime is tail, right? So this is the marginal distribution of HP. So we just add these two things, right? So in this case, we only cares this one. We don't care about this case, right? We just add these two probability that will be marginal probability of this case, right? So, and then what about this case? Same here. If we add these two case, it will be marginal probability of TP. So when penny is tail, right? What about this case? This is marginal probability of this case, and this is a marginal probability, this case, right? This is a marginal probability, marginal distribution. So in this case, we have two numbers, for example. So let's say that in this case, this is 0.25, 0.25, and marginal probability of this case is we can simply add these two cases, right? 0.25 plus 0.25, that is 0.5. And this one, 0.25, 0.25, we get this one, marginal probability. And 0.5, and we add these two, and this is a marginal probability of when the dime is head, and 0.5, this is another, the marginal probability when tail is, a dime is tail. Okay, so do you follow me here? Okay, so, and then when our random variable is categorical, we will have a discrete cases, right? If in this case, dime and penny, we have only 4 cases, right? In that case, we can just simply add them up. So this one plus this one plus this one, or add these two, this will be the marginal probability of a categorical and random variable. But our random variable is continuous. For example, in this case, this kind of distribution, what is the area of this? So we use integral for the continuous, the variables. So, but we're not gonna calculate anything about integral here, okay? So this is marginal. And then conditional distribution is also very important. So conditional distribution is f z given x, right? So this is distribution of z given x, right? So it can be distribution of z given x. It is z and x, joint distribution of z and x over x. So think about this. We have A case and we have B case. Let's say given B event is occur, what is the probability of A? Okay, in that case, PB, this part is given, it's already given, right? So it's right here. And then P, A, and B. And then what is the probability of A and B occur together? Right? So this is right here. So this is conditional probability. Okay, so conditional probability, distributions are found everywhere in statistics and in general linear models. When you learn about regression and ANOVA, you already learn about the conditional distribution, right? So for example, y you have y equals b0 plus b1x1 plus b2x2 plus b3x3. This is regression model, multiple regression model, right? So what is the the conditional distribution of this error or y value. So you can say y given x1, x2, x3, right? So this is regression. When x1, x2, x3 are given, what is y value? Y value is a predicted value, right? So this y is a linear combination of x values. So in regression analysis, there are multiple assumptions in regression analysis. So can you tell me anything about the basic assumption of a linear regression?
Independence.
Yeah, independence. So independence, right? Oh, I'm sorry, independent. How can I say right? Independence. What is independence?
So each observation can't be like essentially taken from the same person.
Yeah, right,
Be...
right. Independence, right? Independent assumption. That means each observation are independent, right? So they are all independent. Or also, another one is x1, x2, x3. Each variables should be also independent. If they are not independent, what will happen? Multicollinearity issue, right? If a multicollinearity issue is occur, your estimation will be biased. Okay, the multicollinearity indicates the high correlation among independent variables, right? So we usually check the VIF and tolerance, right? So if the VIF is greater than 10, which indicates multicollinearity problem, right? So you learned that, right? And then another one is, another really important thing is a normality assumption, right? So this normality assumption is the error variance, the distribution of error variance residuals should follow normal distribution, right? So this normality assumption is about this dependent variable. This normality assumption is not about independent variable. So for example, you have 10 independent variables and some independent variables non-normal. It doesn't matter because independent variables can be continuous or dichotomous or categorical. It can follow normal distribution or it doesn't have to be normal because the GLM is pretty robust to the non-normal of the independent variable, but our dependent variable needs to be normal. Okay, so I will show you the later. So the conditional distribution is really, really important. So, and here, this is for discrete random variables, two conditional distribution can be shown in this one. So in this case, if distribution X and Z, if X and Z are independent, Fx and Fz should be Fx times Fz, which means these two events are independent, okay? So this marginal probability times this marginal probability is disjoint probability, okay? So if these two events are statistically independent, this marginal probability times this marginal probability is disjoint probability, okay? So right here. So do you follow me? Please ask me a question if you don't understand. So this is really important. If two events are independent, So the multiplication of two marginal probability is equal to the joint probability. Okay, so this is conditional distribution. So for example, in this case, conditional probability is like, what is this Z equals head for dime given head for penny, right? So head for dime is what? Z equals head for, this one is 0.5, right? So P, probability of a P is 0.5, right? Let me erase it again.
Yeah.
Okay, so the probability of X equals HP. So this is right here. This marginal probability, this is 0.5, right? And given this occurs, and then what is the probability is the dime is ahead. So this one, right? So our sample space become this case, not whole case, because this is our given situation, right? So this is 0.25 divided by 0.5. So this is 0.5. This is conditional probability of this case, right? What about this case? So given penny is head, right? So this is same, this one, and 0.5, and then probability of dime is tail is 0.25. So this is 0.5, right? So do you follow me? No? Yes? It's okay? Okay. Right. So this is, I'm talking about the marginal distribution, joint distribution, and conditional distribution. If you have X and Z, so marginal distribution is just one variable, X or FC, right? Because we marginalize all cases for that variable, right? And joint distribution is Fx and Z, right? This is like Fx and Z, common area. And then conditional distribution is Fx given Z or Fz given X, right? And then univariate statistics and multivariate statistics, so they all use conditional distribution to estimate parameters. We'll see later. Okay, so here is a statistical independence example. When you have raw data, you can easily conduct a chi-square test. But if you have a summary data, you can still do that using this independence distribution assumption. So if two events are independent, like I said, this assumption is satisfied, right? So P, and this is a joint distribution of A and B, is equal to marginal distribution of A and marginal distribution of B. Okay, this is independent events. And if this is not equal, if these two values are not equal, that is dependent. So which means they are A and B, events A and B are related to each other. Okay. So we can use, so let's think about this case. This is 2x2 table, and one variable is college degree. Okay, so this is college undergraduate and not, there's no college degree. Okay, we have two cases here. And then this one is employment status. Okay, so employed or not employed. And then this is 2x2 table. So 500 people, they have the college undergraduate degree and employed, right? And 200 people, they are employed, but they do not have a college degree, right? And that is 700. And total is 1,000. And in this case, 100, they have a college degree, but they are not employed. And 200, they do not have a college degree and they are not employed. Okay. So and then if you add these two numbers, 600, add these two numbers, the 400, 300. So 600 plus 400, 1,000, 700, 300 is 1,000, right? Okay, so here's my question. What is the marginal probability of employed, PB? What is it?
0.7.
Correct, 0.7, right? Because
Yeah.
1,000 is total. I'm sorry. And then 700. This is the marginal probability of B. What about this case?
Okay.
300.
0.3.
0.3, right? And then this case is maybe 600 over 1,000, 400 over 1,000. So do you follow me? Okay, so here is the same table. And like I said, this is observed case. So a 0.7, 0.3, 0.4, and 0.6, right? And 0.7, 0.3, 0.4, oh, I'm sorry. So this is observed probability. So, and if this is independent, if this, so this is expected probability. If two variables independent, if they are independent, this number should be this one times this one, right? Because if x and z are independent, fxz is equal to fx times xg, right? So 0.6 times 0.4, 0.7 is a 0.4, I'm sorry, 0.42. And this is 0.28. 0.4 times 0.7 is 0.28. And 0.4 times 0.3 is 0.12. And 0.6 times 0.3 is 0.18. Okay. So this is our expected value if these two variables are independent. Okay. But when we calculate our original things, so this is 0.5 because this is observed data. 500 out of 1,000, that is 0.5. And 200 out of 1,000, that is 0.2. And 100 out of 1,000 is 0.1. And 200 out of 1,000, that is 0.2, right? So if these two events or variables are independent, these two values should be same, right? But they're not same, right? So which means, okay, these two events are not independent. So do you follow me? Okay, so next question. If they are not independent each other, so how much they are correlated each other? How much they are related each other? So what is the correlation between these two variables? Right? So next question. This is the phi coefficient. You don't need to memorize, anything, but this is the phi coefficient. So correlation between two binary outcome is a phi coefficient. Okay. And correlation between two continuous variable is what? This is Pearson moment product correlation, right? Product correlation. This is the commonly used R. What about one variable is binary and another variable continuous? What is this?
Point biserial.
Biserial.
Biserial correlation, right? But in this case, so we have two outcomes. This is binary, so this is the phi coefficients, right? So if we add these numbers here, so PA and B is A and B, the 0.5 is joint probability of P and B is this 0.5, and marginal probability of PA is what? PA 0.6. Marginal probability of B is 0.7. If you plug these numbers into this phi coefficient formula, you will get 0.36. This is a correlation of these two discrete events. Okay, so undergraduate degrees and employment status is related. So how much? So correlation is the 0.36. Okay. So and then next question. So is this correlation statistically significant or not? Okay. So we can use that. We can do that using chi-square test. So this is for the chi-square test for phi coefficient. So n is the sample size, and this is phi coefficient square. Okay. So and then it always has 1 degree of freedom. So this test is 1 degree of freedom test. So how many? Let's think about n times the phi coefficient square. In this case, our total sample size was 1,000, and then 0.36 square is 126.98. Okay. So this is our observed chi-square value. Okay. And then this observed chi-square value is greater than degrees of freedom 1 chi-square value. When degrees of freedom is 1 chi-square value is 3.84, right? So that means we reject null hypothesis of no association. Okay. So any questions so far? So so far we use based on the marginal distribution, marginal probability or joint probability and conditional probability, we tested the significance of each event. And then we also computed phi coefficient correlation. And then we can also test the significance based on the chi-square distribution. Okay. So you can do this using R here. So I just typed right here. This is employed 500 and 200. And then I put not employed 100, 200. Okay. And then I combined using RBind function. So which means RBind is row bind. Okay. So I will combine these two vectors, and then I will transform to the data frame. And then I named it employee survey. Okay. But this does not have the variable name. So I add variable name like here. So college, not college, and to the name function. Then if you print it, you will get this one, this table. So first I created a table here, okay? And then to conduct the phi coefficient test, you need to install the the package, okay? And then load it, and then here, the phi, this is the function for the phi coefficient. And then enter this data frame, data, and then digit equals 2. I just suppress the 2 digit. And then you will get this one, 0.36. All right, so it matches our calculation. And then you can also do the chi-square test. It's right here, chi-square. And then you will get significant results. But in real world, you will never do the hand calculation, but you will use R. But I mean, you need to understand how marginal probability and conditional probability and joint probabilities are, related to each other, and how they can be used to the independence test. Okay. Any questions? No? Okay, so let's talk about the multivariate normal distribution. So now this is the univariate normal distribution, right? We talked about this one. So univariate normal distribution is mu and sigma, right? So like I said, exponential and pi, these are all the constant. So this doesn't affect normal distribution. So this normal distribution is defined by these two parameters, right? So this is the univariate normal. And let's look at the multivariate. It looks ugly. It looks really ugly, but it's just almost the same as univariate. Let's look at this part first, right? So only difference is in the univariate, sigma scale was used, but multivariate, covariance matrix was used, okay? Because the multivariate, we have a multiple variable. So for example, 1, 1, 1, 2, 2, 1, and 2, 2. In this case, this is covariance matrix. So we have a multiple correlations or variance, right? So this is used as this sigma sign. This is a covariance matrix. So this is same as this one, right? So they are very similar. Okay, now let's look at this part. This one is this part and this part. This is x mu and x minus mu x. We haven't learned metrics yet, but by define, if you calculate this matrix, it will give us this variance. Okay. So which means this variance value, squared value. So this is equal to this one. Okay. And then also this is covariance matrix. Covariance matrix minus 1. This means this is equal to 1 over this one. And then if you calculate it, actually we can put it here like this. So basically these two formulas are really similar to each other. But only difference is in this multivariate distribution is defined by covariance matrix. Mean vector and covariance matrix. So multivariate, it follows I would say the mean vector and covariance matrix. Okay, so Let's look at this one. So this is X, and this, let's say this is X1 and X2. Okay, so now we can see X1 and X2, we can see some patterns, right? And then also we have some distribution of X based on the X2. So this distribution is what? This is marginal distribution for X2. Do you follow me? And then distribution is, this is marginal distribution for X1. This is X. Okay. What about the joint distribution? So joint distribution of these things will be this multivariate normal distribution, like this. Okay, this is multivariate statistics. So let me show you. We have. Can I use 10 more minutes? Any objection? No, it's fine. Okay, thank
I
you.
just have a class at 1:30.
1:30? Okay, 10 more minutes. All right, thanks.
Thanks.
All right, so this is, I will post this R code. So so you can practice yourself. So can you see this one? Okay, so I installed multiple packages here. So tidyverse, multiple normality, and plot LOY and mass. These are all. So tidyverse includes multiple packages like the dplyr, tidyverse, tidyrl, and ggplot2. So I'm going to use those functions. So I installed that one. And this package is for multivariate analysis. So you need to install this one. And the plot LY. So I installed this one to plot some graph. And a mass, this is for another package for using the multivariate. So distribution. So, and then I loaded them. And then let me create the matrix first. So this, I create the covariance matrix. So matrix and the column and 5, 1, 1, 5, and then number of a column is 2. So I'm going to create 2 columns, and then these are elements, and then I saved these matrix into sigma, and then if I run it like this, so as you can see, 5, 1, 1, 5, right? So I'll use always a column wise. So 5, 1, 1, 5 is a 5, 1, and 1, 5, not 5, 1, 1, 5. Actually, accidentally, the number is the same, but if I change it 2 here, right? So 5, 5, 2, 1, 5, not 5, 2, 1, 5. Okay, so R is column wise. So which means 1 is our the covariance in this case, right? Covariance. So 1 and 1, this is covariance, and this is our variance in this covariance matrix. And then I create the 2 means, 0 and 0. We have 2 variables, and then I assigned 1,000 people. And then I'm going to randomly generate the people using our random multivariate normality function. You can use this function to generate the people. Okay, so and then I set the seed number, and then 1,000 people. And then I'm going to use this mean vector 0 and 0, and then covariance is right here. This one 5, 1, 1, 5. Okay, and then I create this one and then run it. So as you can see, we create 1,000 random variables for x1 and x2. Okay, these are all here, right? Okay, then I make a data frame out of it. I changed it. So using data frame, I change it to the data frame, and then names is x1 and x2. This is 2 variable name. Okay, and then I am going to plot the univariate normal data. So this is our data, and then using the tidy, so deploy R. So from this data, I'm going to create a ggplot and aesthetic mapping. So I'm going to use one variable, x1. And then add geom function, so geom density function. So if I run it, so you can see this one. This is normal univariate distribution, right? And then I'm going to create the theoretical graph from the -3 to +3, and then aesthetic function is x, and then function, this is the stat function. So I'm going to use distribution of normal distribution, okay? And then 1,000 people. So it will create theoretical normal distribution. Okay, it's a perfectly normal, right? So this is, you already know this one, but now I'm going to create the 2D graph. So this is ggplot, D data, aesthetic. So I'm going to use two variable, x1 and x2, and then geom underbar point. So you can make a plot using this function. And the alpha is a transparency. So you can change the transparency of your dot, okay? And then geom underbar density underbar 2D. So this is the, this will create 2D density, this graph, okay? So do you remember? So our, the covariance was what? In our case, I set the
1 and 5.
1, right? So covariance was 1.
Oh, 1.
So it's but variance was 5. So covariance is 1 means it has 2 variable has it's not very highly related each other, right? So if you look at this graph, so they are all random actually. I don't see a clear pattern, right? And then you can also plot the same thing using ggplot ly. It's right here. But if you use a ggplot ly, you can, find a specific data point here. Okay. And then now I'm going to create the 3D. So this is the multivariate. So if you want to see this specific function, you can always looks like this. Question mark, and then type it, and you can see help. Okay, 2-dimensional kernel density estimation. Okay, this function is to create the density function. So I will create the density function based on x1 and x2 and save that in here. And then I'm going to create plot, 3D plot using x, y, and this is density functions based on x and y. So these values will be calculated by the multivariate normal equation. Okay, I just showed you. And then I'm going to add the surface. If you run it, so now we can see, right? So this is a multivariate normal distribution. Okay, so it's a 3D dimension. X, this is X, X1 and X2, and this is density. Okay, but in this case, if I look this one, can you see a clear pattern between X1 and X2? It's pretty circle, right? Because covariance was pretty small in this case. But if I change my covariance here, let me change 5 in this case, okay? Which means, okay, these two variables will be highly correlated each other. Does that make sense? And then I'm going to run it, and run it again. Okay, now you can see here, these multivariate, the normality graph. So it becomes, very peaky, narrow, right? So now we can see very clear, strong relationship between X and Y, right? So this, I'm sorry, this is X2 and X2, X1, and this is Y. So like this. So the multivariate normal distribution is mainly determined by the covariance matrix. Okay, but in definitely the mean vector and covariance matrix. So this is the main difference between univariate normal distribution and multivariate normal distribution. Okay, so I will post this R code, so please play yourself. Okay, right. I'm sorry, I used more time. So, do you have any question? So let me summarize. Today we learned about the different types of the distribution and probability. We learned the marginal probability, density, joint probability, conditional probability. They actually, all these distributions of these probabilities are commonly used for univariate statistics and multivariate statistics. All multivariate statistics is based on joint distribution or conditional distribution. Okay, but the univariate statistics, t-test, z-test, ANOVA, regression, they all use the univariate distribution and also the conditional distribution as well. So we will more talk about the expected value and some, and then the next week I'm going to talk about assessing the normality assumption. So we'll talk about how to assess univariate normality and how to assess the multivariate normality assumption, okay, using R. And then I will briefly review the general linear model, the regression, ANOVA, and ANCOVA, and then we'll move on to the matrix algebra. Is that fine? Okay, so let me stop share. Okay, so please email me if you have any questions. So, and feel free to share your thoughts or questions through the Slack. Okay, I will see you next week. Okay, thank you. Bye.
Thank you, Phil. Thank you.
Bye.
Thanks.
Do
Thanks,
you have
Dave.
any homework this week?
No, not this week.
Thank you.
Okay. Hey, Paul. Shan, are you okay? You follow? Do you follow?
Yeah,
If I-
the R part is a little bit harder than I think.
Our part?
Yeah, but I mean the graph is clear.
Okay, graph is clear. Now
Yeah,
you
the
can see
graph-
the relationship
Yeah,
of these two.
yeah,
Okay,
yeah. I
great.
love the graph. But the syntax is hard.
Syntax is hard. Syntax is hard. Right. But
Yeah.
I will post this oral.
Okay.
Great. So you can play it yourself.
Okay.
All right. See you.
Okay.
Bye.
Thank you. See you.
Mhm.